differential equation, first order model. It is also called application of ordinary differential equation. In mechanical application, in mechanical model, basically there are diverse application of ordinary differential equation. But statistically, we're going to look at an object that is going into the space. An object going into the space. Now, because it's going into the space, there is already a gravitational force of attraction underneath that is rejecting the motion, which is a minus g factor. The gravitational force of attraction that is a pulling factor, and there is a force propelling it upward. And this is the y-axis. Now, we are not considering a projectile object, we are considering an object that is living to the space naturally. So at that level, just like throwing a stone up, at that level, we can develop a relationship, noting that frictional reaction is also opposing the flow of the motion, so that sigma force, the total force along the y-axis, we are going to consider the motion with respect, the force with respect to frictional effect, friction. Let's say force mu, the frictional factor. While we are also going to consider the gravitational force, Fg. Now the gravitational force, so we are looking at mass multiplied by dV/dt. Mass times acceleration according to Sir Isaac Newton is equal to minus CV minus mg. Now take note that this is the relationship for the frictional action of the object in space. Mass multiplied by gravitational force of attraction is negated because it is going upward. So this is a model, a first order model, mathematical model of a mechanical object on space. Now in mechanics and properties of matter, basically this relationship exists, and we are going to transform this first order model to a typical first order linear differential equation, which is dV/dt equal to minus c over mv minus g. As we are dividing through by m remains here. Crossing to this other side, if we prefer, or making it a linear first order differential equation, we have dV/dt plus c over mv equal to minus g. Take note that as it's crossing, it turns to plus. The linear first order differential equation has emanated. Now, this is linear first order differential equation, which the solution expression can be linked to dy dx of a first order linear differential equation plus py equal to q, a linear first order differential equation format in ODE, and which gives a solution formula of y exponential integral p dx is equal to integral q exponential integral p dx differential x plus arbitrary c. This is the solution formula to the first order linear differential equation of dy dx plus py equal to q is y exponential integral p dx equal to integral q exponential integral p dx dx plus arbitrary constant c. Now we can further this operation in cos of q to relate it, to have that from that relationship dv, we are now going to see, since it is dv, the equation ab initio is dV/dt plus c over mv is equal to minus g. Let's call this equation 1. This equation 1 can be likened to a first order differential equation that just reflected at the downside now. And this relationship will culminate at v, which is the velocity. Velocity is a function of time, is now equal to y when we are translating from the first order linear differential equation. While also we are having our p is equal to c over m from the linear first order general equation, and while our q is equal to minus g. When this culminates into a model, it gives us v as function of t exponential integral c over m dt is equal to integral q, which is minus g exponential integral c over m dt differential t plus arbitrary constant c. So this gives us voltage function of time exponential c over mt is equal to minus g, which is constant, integral exponential c over mt dt plus arbitrary c, when this is integrated and this is integrated. Now, when we integrate c over m dt, you have t. So that furthermore, velocity is a function of time exponential c over m. C over mt is equal to minus g dot integration of exponential c over mt, will just gives us m over c exponential c over mt plus arbitrary constant c. Now, when we relate it, we have already seen here c, which is a constant with respect to the fluid effect of the flow of the object in space, the fluid flow. So we can call this k. In order to avoid ambiguity, we can also call here k. We can call here k to avoid ambiguity. Now, that is to say, if we are calling here k, it is to leave the frictional constant effect. This is a frictional constant effect on the space, because the object is being opposed based on the flow of air, the resistance to air motion, which is a fluid mechanics concept. So at the end of the day, we have velocity function of time exponential c over mt is equal to c over m. C over mt is equal to, now since this has been integrated and we are having the inverse of it, because based on integration format we have minus gm over c exponential c over mt plus arbitrary constant k. So we could divide through by this, and that finally gives us velocity is a function of time is equal to minus gm over c plus k exponential minus c over mt. You can hand it here or rearrange it properly to have velocity is a function of time is equal to k exponential minus c over mt minus gm over c. Now this is a mechanical proof of an object that is thrown into space when we are considering the air resistance factor. The air resistance factor has to be considered, and we have to note that the gravitational force of attraction was being opposed, and that is the essence of the negative sign attached to G, not plus G. But if the object was to be coming down like a mango that is falling from a tree, it has to be plus G.